Okay, let's get started. Hi, everyone. Thank you so much for coming to my talk. I hope you are having lots of fun today. I am Alena Hall, and I'm going to talk to you about distributed systems for stream processing, like Apache Kafka and Apache Spark. So every system has data. Whether it's persisted or not, every system has it. And data is generated by basically every single thing around us. Whether it's something you're doing on your phone, using your credit card, all of those sensors and IoT devices around us, they all generate large amounts of data. And when we as engineers start thinking of building distributed systems that involve a lot of data coming in and out, we have to think about the flexibility and architecture of how these streams of data are being consumed and produced. So on earlier stages, we might have just a few components, for example, a web application that generates some user actions. And we might have a database that is supposed to store all this data. So we have a producer, a web app, and a consumer, a database. And at this point, there is usually a one-to-one mapping between the producer and the consumer. But when our application grows, we start introducing new software components because our infrastructure grows. For example, we might need a cache or some data analytics system to improve the user flow. And then this requires our web application to send the data to all those new systems. What if we want to introduce a mobile application? This is a new additional source of data, which it becomes really hard to keep track of all those sources. So eventually we grow and end up with a lot of independent data producers, a lot of independent data consumers, and many different sorts of data flowing between them. And there are challenges. How do we make sure that the architecture doesn't become too cumbersome with so many producers and consumers? How do we prepare for the need to scale and adjust on changes in data rates of all the events coming in? And how do we ensure that the data is persisted durably so that we don't ever lose any important messages? So let's look at Apache Kafka and Apache Spark. And just a quick show of hands, who used Apache Kafka or Spark? OK. So for those who did not use it or did not hear about it, I'll do a quick overview so that you know what we're talking about. So Kafka is an open source stream processing system. It is used for building real-time streaming data pipelines that can reliably get data between many independent systems or applications. And it also provides like a unified layer with a high throughput, low latency, and horizontally scalable platform that is actually used in production by thousands of companies. What it allows is publishing and subscribing to streams of records, and also storing the streams of records in a durable way, and also a fault-tolerant way. So now, to understand how Kafka does those things, let's look at a few concepts here. Kafka is run as a cluster on one or more servers that are called brokers. And they can be in multiple data centers. It also uses Zookeeper to store metadata about brokers, topics, and partitions. The core abstraction that Kafka provides is a topic that represents a stream of records. And you can think of a topic as a distributed, immutable, append-only partitioned commit log, where producers can write data and consumers can read data from. Oops. OK, it works. So in each record in the topic consists of a key, a value, and a timestamp. A topic can have 0, 1, or more subscribers that can consume data written to it. And Kafka also durably persists all of the messages that are coming using the configurable retention period. And I think by default it's sent to it's saved a few days, but you can change it. So topics are partitioned And each partition in a topic is also an ordered and immutable sequence of records that is continually appended to a structured commit log. And the records in partition have offsets. It's a number that uniquely identifies the record. And each individual partition must fit on a server that hosts it. But at the same time, a topic can have many, many partitions distributed across many brokers, and this allows storing arbitrary amount of data in Kafka. Also, each partition can be replicated across configurable number of brokers for fault tolerance. And each partition can have a role, like a leader that accepts read and write requests for partition, and a 0 or more partitions can be followers that just replicate data written to the leader. And also, each broker can act as a leader for some partitions or as a follower for others, which makes sure that we have even load balancing. Now let's explore how we can actually create a Kafka topic. And I'm using Azure HDInsight as a service for Kafka. And I'll tell you about this in a bit. So here I'm connecting to my HDInsight server Kafka cluster. And I'm using create topics command. Kafka topics create, topic name, number of partitions, replication factor. And we can check that the topic exists by running the list command. That would tell us whether the topic was created or not. So here it is. So that works. Now, after we have a topic, we can have many producers and consumers working with the topic. Producers can publish data to the topic, and consumers can subscribe to various topics and receive messages from them. And consumers can act as individual consumers, or they can be a part of a consumer group that would distribute the reading load across consumers. So Kafka is great as an event ingestion system, making it work with many producers and consumers in a scalable and durable fashion. Now, sometimes we need a system that is able to process streams of events as soon as they arrive on the fly, and then perform some action based on the results of the processing. It can be an alert or notification or something that has to happen in real time. So now let's talk about Apache Spark and how it can help us. Apache Spark is an open source project for large-scale distributed computations. You can use Spark to build real-time streaming applications that do processing or transformations on streams of data. It is kind of similar to MapReduce, but it is also more powerful and much faster. It supports more operations than just map and reduce, and it also operates primarily according to directed acyclic graph execution model. Sorry about that. Talking about what Spark is, and I was mentioning that it operates according to directed acyclic graph execution model, which is more flexible than MapReduce. And also, Spark operates primarily in memory. And as of the latest release, Spark not only supports the micro-batch execution model, but also continuous, which makes it even faster. Spark can be used on a variety of schedulers. For example, it can run on Yarn, on Apache Mesos, and Kubernetes, and it can also run in a standalone mode. So things you can do with Spark are Spark SQL, batch processing, stream processing, machine learning, graph computations, a lot of things. So, and if you have not seen a Spark program before, this is how it might look like. This is a very simple one, where it reads data from some remote location, like HDFS, and then we perform a series, like a pipeline of distributed computations, and in this case, it is word count, which is simple. And after that, the results are saved to the remote location as well. So just that you get a notion of how Spark jobs look like. So how does Spark work? We can submit jobs to run on Spark. And on a high level, when we submit a Spark job, it creates an operator graph and sends it to a scheduler. And there, the operators are divided into stages of tasks, which correspond to some partition of our input data. Spark has physical nodes that are called workers. This is where all the work happens. There is also a process called driver that manages the entire job and execution of tasks. And there are executors. Those are distributed agents that run on worker nodes, and they execute tasks, which tasks are just the smallest individual units of execution for our job partitions. So now, Kafka is great for building durable and scalable ingestion of streams, of events coming from many, many different independent consumers and producers. Spark is great for real-time processing of data, including streams of events. Now how do we combine using Spark and Kafka together? Both are open source technologies. We can use them on Azure. You can set up virtual machines and build all the infrastructure if you want to manage the machines. Or you can use managed services, where Azure actually takes care of the infrastructure. And Kafka can be used on top of HDInsight, and Spark can be used with Azure Databricks. There are detailed instructions of how to create the clusters for Kafka and Spark on Azure online, so I won't really show this here. Instead, we will spend time looking at interactions between those two and understanding the architecture of streaming real-time systems a little bit more. You can also peer those clusters together. They have each virtual network, and we can peer them together to make sure that they can talk to each other. So, and I'm going to show you quite a few examples, but I already have a Kafka cluster in HDInsight. I have an Azure Databricks workspace with Spark cluster. I have peered their virtual networks together, and I'm going to be using public sources of data, including Twitter data, but also public data sets saved on Azure Storage. So let's take a look at interactive environment that I'm going to be using at first. So this is Azure Databricks portal, and let's go to clusters section. Here's my Spark cluster. And let's look at notebooks. There are quite a few notebooks, and when we choose to click on one of them, there are code cells that we can execute. So this is what we're going to be doing. Now let's look at the real practical example. Imagine that you are in charge of a bike share company, and you have quite a few competitors in your city, and you want to make sure that your customers get the best experience ever. And as an example, I'm using Portland's bike sharing company, and there is a Twitter hashtag called BikeTownPDX, where riders can share thoughts about their rides or any information. And in these situations, what we can do is build a streaming system that would create a stream of tweets about the bike share, and use Kafka to ingest this data, and use it as a source for Spark to get the stream of tweets and analyze it. This way, we can make sure that if there is something happening, let's say if some rider has issues with his bike, we will be able to notice it in real time and react on it. So help them, or if there is a good information, we can just like the tweet. So we want to make sure the customers have best experience. Now let's look at a Kafka producer for this. So I'm in my bike Twitter producer notebook, and I'm connected to the cluster. Now I'm importing some libraries to work with Kafka, and I need to connect to Kafka brokers to make sure that I can send tweets to Kafka topic, which is called Biketown Tweets. Now I'm also specializing my serializers, which is just a basic string in this case, and providing send event function, which will just put a message in the Kafka topic. Now I also need my Twitter access keys, and I needed to programmatically access a stream of tweets. And what I'm doing here, I'm just sending tweets by this hashtag. to my Kafka topic that can be later consumed by any applications. So tweets are coming in. So that's good. That's working. For now, let's cancel this producer. And let's look at Spark Consumer. So even though Kafka topic can be consumed by many applications, Spark has a direct connector from Kafka to Spark. And let's see how it works. So this is another notebook. And here I'm also connecting to Kafka brokers, but this time to read data from Kafka. And the format here is Kafka. It can be different. It can be event hubs. If I'm using other input system, it can be anything. And I'm subscribing to a topic called Biketown Tweets and getting the latest data. Because I don't want to get the data from the beginning of the history of the topic. Now let's see if the data is coming in, executing the append function to the console. Here. So the data is not coming in because we canceled the producer. Now let's get the producer and start it again. So after it's started, let's go back to the consumer, and we should see data. Here is the data, and it's coming in the binary format because this is how Kafka stores the data. There is a partition, offset, timestamp column, and also a value column, which is the one we need because this is where the actual content of the messages is. And what we can do is we can cast it to a string type so that we can actually read it. And let's repeat the write so that we can see what data is coming in. So here's our data. So that works. Now we're receiving the actual messages. But receiving messages, of course, is not enough. So we want to analyze the stream of tweets and determine which ones we need to act upon. So whether we need to reply to a user and fix something. And I'm using sentiment analysis APIs and I'm defining some classes like getLanguage and getSentiment that I can do processing on my streams. This is a user-defined function that will add a column to our infinite table, and we will be able to see the sentiment of each tweet. So yeah, so after that, we will just, again, print out the entire stream. Yeah, so here is our stream, and here is the data. Here, 1 will mean that the sentiment is positive, like so many awesome bikey things. This is definitely a positive tweet. We can just like it, probably. And if the sentiment is closer to 0, that means we'll probably need to do something about this tweet, because somebody might be unhappy. Here is 0.22. Somebody is scared to ride through downtown, so we will reply to this tweet. Cool. So this is how it works. Now, with this kind of system, we can keep track of streams of data on social media from many, many sources, not only Twitter, from every single source that we can imagine. And we can do real-time transformations and processing on those streams to make sure that we are aware of what's happening. We can react on those things. Let's look at another example. And this time, I'm using open data from Portland's bike share system that is publicly available. And it has statistics of all the rides that happened since the system started functioning. And a little bit about how the system works so that we can better understand the example. There are bike hubs with racks from 14 to 18 bikes. And users can just grab a bike from the hub or from the street and then make a ride, park it back in the hub, or just drop it off anywhere on the street. People can be subscribed and pay per month, or you can pay per trip. So this is how it works, basically. Now, I saved all the data in my Azure storage account, basically CSV files like this. And now let's imagine that we are retrieving this data in real time. So of course, we can imagine that we're in charge of this company, and we have all this data coming in from real bikes with tracking devices. But because we don't have a company, we'll just imagine that the data is coming in, we'll use the statistical data. And why would we do that? Because it's important to watch this data, for example, to make sure that the bikes are evenly distributed. If we notice some spikes, we notice that they're being left at one place, or some bikes hubs are empty, we would want to redistribute the bikes and make sure that system is evenly balanced. So if we don't do this, we will just keep our system unorganized. So let's see how we can improve the situation. Now let's look at Kafka Producer. In real life, we would have all this data coming in from the bike hubs, from the bikes itself. They would publish data to Kafka topic. But here, I will write a generator that would send the data from the statistics. So I'm connected to my Azure storage to get the data. So now let's see, after we get the data, let's see what the format of the data is. We can print schema. So here is what fields are: route ID, payment plan, start hub, end hub, distance, duration of the ride. And we would want to send these messages in a topic and make them consumable from Spark. So let's make it JSON format. Let's convert all the data to JSON and see what real messages published to Kafka topic would look like. Looks right. So then we would need to connect to a Kafka topic again and send the bike trips data into the topic. Let's start our producer, sending the message. And we can also track the progress if we expand the Spark jobs here and see that 12 of them are running. We can look at the log files. For example, choose this one. And those are events that are being sent. Cool. So now let's look at the Spark consumer. Let's connect to the Kafka brokers from the reading side of it. Now we're subscribing to the bike trips topic, converting it to the Kafka format. We're getting the value. And isStreaming function is really cool because it allows us to see if the data is streaming or not. Now, let's display the data coming in. So those are the raw messages coming in. It's good that we're getting data, but we need to convert them to necessary types for convenience purposes. So now we have them converted to necessary types, which is good. And the next thing we can do is we can see what the actual data looks like. We can use the display function. It should show us the table that looks like a table, but for real, it's the streaming data. Table is being constantly updated at an input rate, processing rate. And this is what the data looks like. If we want, we can output it in a raw format like this so that we can copy it, just if it's convenient at some points. And what we can do next is we can watch number of bikes departing from each hub. So we would see the count of bikes departing, and we will notice that if some number is really big, or if so many bikes are being dropped off at the street, we would want to redistribute them. So let's see what we got. Here we have batches. So first of all, the most popular start station is at 18th and Flanders Street, 6 bikes departing from it. But then we noticed that no hub is the most popular station. That means people are just grabbing bikes from the street, which is good. But now the second popular is Everett and 22nd. If it becomes even more popular, we might need to add up more bikes to it. So this is the kind of things that the system allows us to do. But this is just one example. There can be many, many things that we can keep track of and check. So what we achieved here is a balanced system where we watch all the trips and get real-time insights about when we need to take action, as well as when we need to reply or when we need to provide help for users on social media. And these are, again, just a few examples. In real world, we'll have even more data sources, even more things to watch, and even more actions to take. So with Kafka, we don't really need more levels of bringing data from one point to another, because it can act as a single layer for data ingestion between many, many producers and consumers independently. It can handle it reliably. It has durability to save all the messages. And it is very fast. And Spark, it can consume streams of events from Kafka for processing, transformations, machine learning, with a goal to notify us when we need to ensure the success of our business and take action. So here are some of the resources that might be useful for the future. How to get started with Apache Kafka, with Spark. There is an article of how you can use Kafka and Spark together on Azure. How to create HDInsight Kafka cluster using Azure Resource Manager, or how to create Kafka topics. You can follow me on Twitter and on GitHub to ask any questions. And this is the last slide. Thank you so much for listening. I'll be available for questions at the lounge, because I think it's time for the next speaker.